All right, let's jump right in. In the next few minutes, we're going to build a mental toolkit that's going to completely change how you look at technology. We're talking about sensors. You know, the nervous system of our entire modern world. We're going to break down the 4 essential ways to classify pretty much any sensor you'll ever come across.
Look, it is so easy to get lost in the sheer variety of sensors out there, right? But what if I told you there's a simple framework to understand all of them? Well, that's exactly what we're about to do. Give you a clear method to turn all that complexity into clarity.
So here's our game plan, our roadmap for this quick study. We're going to look at sensors through 4 different lenses. First up, the signal they put out. Then, we'll talk about their power source. Third, we'll get into their mode of operation. And finally, we'll cover the most intuitive one, the subject they're designed to measure.
Seriously, if you can master just these 4 ways of thinking about sensors, you'll have that powerful mental toolkit ready to go. So let's dive into the first one.
Okay, first up, classification 1, the signal. This is all about how a sensor talks. Is it speaking in a smooth, continuous way, analog, or is it speaking in the crisp, clear language of computers, digital?
Here's the core difference. On the one hand, you've got analog sensors. Think of these like a light dimmer switch. They give us a continuous, flowing signal that's perfect for capturing every tiny, gradual change. On the other hand, digital sensors speak in discrete steps, zeros and ones. They do the conversion to digital data right inside the sensor itself, which makes them way less sensitive to noise and super easy to hook up directly to a computer or a microcontroller.
And you see this play out in the real world all the time. An analog thermistor, for instance, has a resistance that changes smoothly as it gets warmer or cooler. A digital temperature sensor, though, just gives you a number. It says, the temperature is 25.3 degrees Celsius, period. It's really the difference between seeing a wave and just getting a number.
All right, our second classification is all about the juice, the power. Does the sensor make its own energy, or does it need a little help from an external source? This is the classic difference between active and passive sensors.
Yeah, it really just comes down to energy. Active sensors are the self-sufficient ones. They actually take energy from the environment, like heat or pressure, and convert it directly into an electrical signal. Passive sensors, though, they need an external power source, what's called an excitation signal. They take that power and then change it in some way to give you a measurement.
So a thermocouple is a perfect example of an active sensor. It literally creates its own voltage just from a temperature difference. A strain gauge, though, that's passive. You have to pass a current through it to see how its resistance changes under stress. Now here's where it gets interesting. Remember how we just said a strain gauge is analog? Well, it's also passive. This shows you that a single sensor can fit into multiple categories. It all just depends on which lens you're using to look at it.
All right, we're halfway there. For our third classification, let's ask a different question. How does the sensor actually get its reading? This brings us to its mode of operation, null type versus deflection type.
This one is really a tale of precision versus simplicity. A null-type sensor is kind of like an old-school balancing scale. It works by comparing what it's measuring against a known value, until the difference between them is 0, or null. The actual measurement is the known value it used to get that perfect balance. It's incredibly accurate. A deflection-type sensor is much more direct. It just measures how much something moves or deflects, like the needle on a tire pressure gauge. It's simpler, for sure, but maybe not as precise.
So for a null-type system, the classic example is a Wheatstone bridge, which you'd often use with a strain gauge to get super accurate readings. For deflection type, just picture that classic Borden tube inside a pressure gauge that physically uncoils as the pressure goes up. It's really the difference between a very precise balancing act and a direct, visible movement.
And that brings us to our fourth and final classification, which is probably the one you're most familiar with, even if you didn't know it. We call it the subject. Or to put it simply, what is this sensor actually measuring?
This category is basically a snapshot of all the incredible sensory powers we've managed to engineer. You've got mechanical sensors that measure force and pressure, thermal sensors for temperature, optical sensors for light, chemical sensors that can literally smell certain gases, all the way to biomedical sensors monitoring our heart rate. The range of what we can measure is just, wow, it's always expanding.
So why does this framework matter so much? Well, it's all about making the right choice. Knowing these classifications is absolutely key to picking the right sensor for the job, one with the right accuracy that's compatible with your system. This isn't just some abstract theory. This is the practical foundation for building everything from a smart thermostat in your house to a rover exploring Mars.
So there you have it, 4 lenses to help you make sense of any sensor.
But as technology keeps racing forward and sensors start merging with AI, it really makes you wonder, what's the fifth classification going to be? Maybe something like cognitive sensors or predictive sensors? Definitely something to think about. Thanks for joining me for this explainer,